problem with some of the fundamentals, so to speak, please see me as soon as possible. Okay, we have office hours today. We have office hours tomorrow. By the way, some of you keep, forgetting that sticker on my office appointment only. That's not for you. Okay. So office hours means you can come anytime during that office hour. There are two. Okay. Take advantage of it. Please take advantage of it. Yes.
Are you giving us back the midterm paper?
I'm sorry.
Midterm?
What about the papers?
Yeah.
Should you get them back? I think they do return them to you. Yeah. In the. Yeah, probably. Yeah. They should be given back to you. Okay. All right. So, yes, quick.
Grade included in the grade we calculate?
I'm sorry?
Is the group midterm grade included in the grade?
I think so, yeah. I will double check, but my understanding it is. This is the first time they do this business, group midterm. It was last semester? Okay. So it's the first time I teach it. And some of you, please guys, some of you asked me a question about this problem in the book, where there's a plate and there's another plate here, and this are connected to each other, right? And grounded. And then there's a plate that is connected in the middle, right? Like this. Such that this is D and this is 2D, something like that. These look like two capacitors, correct? For those who solve the problem. Are they two capacitors in parallel or in series? In series. How many people say they're in series? How many say in parallel? What's the rest of you? What's that? How many solve this problem? By the way, if you did not solve it, I'll have it in the final. I promise you. Okay? Check it out. Please look at this carefully, because you're being told that there's a Q here. There's a Q that is placed right here. I'm going to say just a quick word. In these kind of problems, capacitance type problems, we either work with the voltage, knowing that the voltage is not changing, or we have some idea of how the voltage is distributed. Okay? But what I want to say about this is that this is actually, if I do this following schematic here, can you answer the question? Are they in parallel or are they in series? So if you have a resistor like this, and I have another resistor that is connected to it like this, are they in parallel or are they in series? Both. Okay? They're both, right? Does that make sense? They're in parallel and they're in series. This is a very unique situation that can happen to two elements that are the only ones in the circuit. The only ones. Because if I were to connect other things to this circuit, they're only parallel, right? Someone had a question?
How would you add them? They're both in parallel and series.
It's the same thing. If I were to, I don't need to add them actually. I don't need to add them. You know why? That's a very good question. It's a very challenging question. You know how professors, when they don't know how to answer a question, they say, good question. No. I cannot and I will not. Why? Because it ceases to be a circuit. That's the unique situation about this. Because you will end up with an equivalent, so-called, hypothetically, an equivalent capacitor with two wires sticking out. Where are they connected? Nowhere. Okay? So this is a unique situation where you cannot do that. All right? Now, if we had these two connected to another circuit somewhere here, this is a circuit, then I can do that because there is continuation of the current path. Okay? So now you learn something very important, right? How professors answer questions. All right. So today I'm going to talk about the following. Okay, this is our plan for today. This is not cooperating, so I'm going to leave this aside here. The plan for today is to understand what happens when we have a current sheet. We have a current sheet. We will introduce the concept of surface current density. Surface current density. We're going to draw a parallel to charges. Charges, we had charge, Q. We had charge, surface charge density, right? We had volume charge density. And what else? And we had line charge density. Are we going to see the same thing happening for current? Not quite.
So, why should we need to solve that question?
This one?
Yeah.
I will solve it. I can do it later, not today. I mean, you can come in office hours, we can discuss it, but I don't want to take away from the lecture, okay? It's not that hard to solve, okay? If you start with the voltages here, it's not that, okay? So anyone who wants to follow up on this, please, office hours immediately after the lecture. So the current sheet, okay. So let me draw what we mean by a current sheet. Please understand this very carefully. There's no such thing as, please guys, unless you're taking notes. Are you taking notes? Okay. If you're taking notes, you can leave it. There's no such thing as a current sheet in reality, okay? It is an approximation. I was never told that when I studied this course for the first time, okay? It's an approximation. So what do we mean by that? So I have an infinitesimal thickness. Infinitesimal thickness. In other words, if you imagine there's a thickness to this sheet, it is almost zero, okay? And I'm going to have a current. I'm going to have a current that is, I chose it to be coming out. I chose this to be, yes, coming out. So here is a current that is distributed throughout this sheet going on to infinity. It's an infinite sheet. The current is coming out in your direction. So I'm going to put a dot, okay? Coming out. So this is my coordinate system. This is Z hat, and this is Y hat. So X is out. The current is in the X direction. So I'm going to put here X hat, okay? So, all right. So this is looking onto the YZ plane. If I have a perspective view of this current sheet, it's going to be like this. Of course, it's an infinite current sheet, but the current is going in this direction, okay? This will be a Y, Z, and this will be X, okay? So this is a perspective view, and this is a side view. All right. So I'm going to, now, how do we create something like this? Some of you might be interested, how in the world do we create something like this? So I'm going to define JS here. JS is a vector. S stands for surface current density, and it's pointing in one direction. How do we create something like this? I'm going to come here and show you a possibility, one way to create something like this. So I have a sheet, huge sheet. I come here and put a voltage source and connect it right here, okay? So there's an I that comes, I can put plus here and minus here, it doesn't matter, we understand it is a voltage source. I am kicking out an I out of this voltage source. This I going to enter the sheet and going to distribute itself. In reality, you don't expect the current to be uniform, the density to be uniform, right? You cannot expect the current to be uniform, but we will assume for the purpose of this illustration, this example, that the current is uniform. Current density to be precise. Current density is uniform. So if I'm here, 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 anywhere, I see the same current density. What's the definition of the current density? Js, that's my current density, is I, the entire I that is traveling on the sheet, the entire I divided by the width of the sheet, okay? Divided by the width of the sheet, okay? If I have infinite sheet, the I will be infinite, D will be infinite, but the ratio of these two will always be constant, okay? So this is the surface current density. My goal right now is to find out what is the field, the beam, the magnetic field on top, which means for Z greater than 0, and the magnetic field for Z less than 0. Okay? The tools that we developed thus far are useful. The physics is somewhat different. Okay? It's somewhat different. So I come to this point right here, and I take a line vertical to this current sheet. So this is a current sheet. What is the unit of the surface current density? Amp per meter. Don't make the mistake, amp per meter squared. There's no such thing as amp per meter squared. Amp per meter squared is what? What is amp per meter squared?
The J we have.
The J we have, the physical J, the real life J, the current density, okay? There's current density, and there's a surface current density, okay? There's nothing beyond that. There's no such thing as volume current density or line current density.
Why do we call it surface while we're just dividing it by a length, not an area?
Yeah, because it's traveling on the surface. Yeah, see, it's traveling on the surface. In other words, the current, this is my surface. Above it and below it, there's nothing. There's no current. Okay, he's first, and then you go second. Go ahead.
This is not something that actually happens in reality. How does this relate to physical?
The closest thing to reality is this, is what I've done here, is that I have a voltage source, and I connect it across a sheet. So right now, the current, there's an I that is coming here. It will distribute itself throughout the sheet. Here, I will assume it is uniform density. You will see why this is useful, actually. But doesn't this remind you of the charge, of the charge distributed on a sheet? There, we divided Q by A squared, by the area. Sorry. Divided the Q by the area. So Coulomb meter squared. Okay? Here I take the current amp divided by the width, this width, to get the surface current density. All right, so let's go fast right now. So I take one of the current, I imagine that this is composed of many, sorry, go ahead.
Why is that a vector?
Why is it a vector? I forgot to put here x. Because it is moving in one direction, in a certain direction. I'm sorry? Yes, absolutely. Okay? Because you see, I don't want to preempt what we're going to do next, but we're trying to isolate the source. We're trying to have a localized source. That's where we're heading. I is not localized. You see, I is not localized. J is localized. Let's look at this problem here, or here. I have a source that is connected to this and creates that current. Gents, this is really important concept, please. I have a current that is feeding this sheet. Okay? Guys, please. Please. Okay? I have a current that is feeding this sheet. Can you localize I? Can you say, at this point I have I, at this point I have I, at this point I have I? No. But I can localize, if I work with J, I have a local description of the movement of charge. Do you see that? So if I come here, I have a J traveling in that direction, right?
But don't you also have an I traveling in that direction?
I do have an I, but J is a local information. I is not.
What do you mean by localized?
Because here the density in this example is uniform. But I can have a problem where the density is not uniform. You see? Possibly. Yeah. You see? If we were to look, if we have an I that can see the current, okay, like a numerical code, let's say, you will see that the current distribution is not uniform. There's a lot of current coming here on the edges and very little current in the middle. So the current density is not uniform across that surface. So I doesn't help me, right? Because I is feeding the entire sheet. You see? But locally, J is going to help me. One more important piece of information. Why am I doing this? Because we're going to get to Maxwell's equations. Maxwell's equations represent a local, point-wise electromagnetic phenomenon. It does not describe everything in the world. It describes what's happening at a point. Okay? That will allow us to divide and conquer a huge problem. We'll see that later on. Okay, so now we understand the problem. We understand that we have a new description that is useful. Now I'm going to find the field at this point due to this distribution of current. So I take one here, let's say away by distance d, and I take its mirror image on the other side of this hypothetical divide. This current here will give me a field that is pointing orthogonal to the line that connects the observation point and the current source, right? And this one will give me the same thing. So I create another line that connects the mirrored image of this one, d distance away. It will give me a magnetic field that is orthogonal to the line that connects them. The sum of these two will be parallel. Geometrically, I can find out that the sum of these two will be parallel to the sheet. In which direction? In which direction? In direction orthogonal to the direction of the current. The current is coming out. The sheet is going out like this. The B field will be parallel to the sheet, but what? In a direction, this is the current, in a direction orthogonal to the direction of the current. Okay? Right, so how do we find this? Remember, when we had the problem of Q distributed over a sheet, how did we find the field above and the field below? We used Gauss' law. Here we use Ampere law. Okay? We use Ampere law, and we take an area like this, or a contour, I should say, a contour like this, and I integrate. I will write. We don't need this anymore. If I find an eraser, then I will. There. The concept of a surface current is incredibly fundamental to electromagnetics, to the broader electromagnetic field. Okay. Okay. So I'm going to apply Ampere law. Ampere law. Okay. Integration over a closed contour. 1 second, please. Integrating B over a closed contour, which is the contour right here. Okay, that gives me the I enclosed within the contour, multiplied by mu naught. Yes?
Could you just explain the direction of the arrows?
You see, if this is coming out, so if I have a current that is coming out, I grab that current. Imagine there's a current coming out. I grab it with my hand, make my thumb pointing in the direction of the current, then the B field will be the direction of the fingers. Okay? So if the current was going in, it will be pointing in the opposite direction. Okay? Before I continue with this, if I were to go here, will the field be different along this contour? Why not? If I move along this contour on the assumption that this sheet is infinite, on the assumption that the sheet is infinite, I'm going to have a uniform magnetic field along this side of the contour. What about along this side of the contour? The magnetic field is 0. Okay? What about along this side of the contour? Symmetry. It will be pointing in the opposite direction. Okay? So, all right? So what is the I? What is the I? Let me give myself room here. Before I go to the I, so we said that B is constant. B is constant, right? So I'm basically integrating B dotted with dy. B dotted with dy. Along, I will divide this contour 1, contour 2, 3, and 4 over contour 3 plus B dy minus, okay, the first one here, B is pointing in this direction. I'm integrating in that direction. Just one second. B is going in that direction. I'm integrating in that direction. So B is in the minus y direction. I'm integrating in the minus y direction. So the minus and the minus cancel. Here, I'm integrating in the positive, and B is pointing in the positive.
B isn't 0 in the vertical part of your loop, right?
Yes.
It's just
B is, there's no B that is pointing in that direction, okay? Because of the argument that we
There's
just
a B
described.
going.
There's a B, yeah. There's, as we move along this contour and this contour, B is pointing this way along C3, B is pointing this way along C1, and it is constant along this contour. So these two will contribute to B dotted with this distance. Let's say it's 2D, and 2 of them, right? 2 of them. D, twice the D multiplied by B, twice the D multiplied by B, and that's what we end up with here, 4DB, right? Right? Just one second. Let me make sure that my algebra is perfect. Yes.
Why don't they cancel out? It's one thing.
Okay. I rushed through this, but let me explain and then I'll correct if I made any algebraic mistake. B is pointing in which direction here? This way, right? B is pointing in which direction here? I'm integrating this B along the negative direction, correct? So B here has a value of B minus y, correct? Right here. I'm integrating in the negative y direction, so the minus disappears. Here it's the opposite. Here, the value of B is B y hat because it's pointing in that direction. I'm integrating along the positive, so the by will be dotted with y hat, and I'll end up with a B, okay? So I can just symbolically leave it like this, okay? And we know that we'll end up with this, okay? Now, finally, what is the last thing I need to do? Is to find out what is the I, this I, that is encircled by the contour, right? I need the I that is encircled by the contour, and that will be the surface current density multiplied by 2D, right? Multiplied by 2D. So I'll end up with here. So I'll bring this right here. I have JS multiplied by 2D. The 2D and the 2D cancel. So B equals JS divided by 2. JS, I forgot one thing. What did I forget, guys? The mu naught. So I have a mu naught here, and the mu naught goes here, and the mu naught goes here. Okay, so I solve for the B. It's a very simple, very simple exercise. Very important, though. Very important, though. So did you notice that this B, so finally, to put it in a vector form, as a vector, I can put B equals JS divided by 2 mu naught. Okay? I ran out of room here, so I have to do it there. Actually, I'll do it right here. So finally, B as a vector will be JS mu naught divided by 2 minus y hat for z greater or equal to 0, assuming that z equals 0 is right here, according to this coordinate system. And I have plus JS mu naught y hat divided by 2 for z less than 0. Okay? Some of you might say, why don't you have the minus, the equal sign here, not here? Okay? Is that a good question or not? Is that an interesting question or not? There's no such thing as a good question. In my opinion, there's such thing as interesting question or not. Yes?
Is it related to boundary conditions? Or?
You're cheating. You're right. It is related to boundary condition. We're going to do that in a few lectures down the line. But let me explain, now that we talked about it, let me not explain the boundary condition, explain something very important. Really, it's really interesting to see what's happening without studying the so-called boundary conditions. Okay? Yes?
So for example, if the sheet had 0 resistance, so then the current would be infinite. So the magnetic field is infinite?
I didn't talk about the sheet characteristics. I only said,
I know, but it's like a question.
I will answer. I only said that there's an I going like this. There's an I going like this. I'll come to you. I'll satisfy you, hopefully. The I is going in that direction, okay? The I is going in that direction. What is assumed that there's something holding the I? Do you see that? I mean, the only I that exists in space is that when you have a lightning, right? And that lasts for a few microseconds. But for this example that I talked about, you need a sheet to hold the eye. Otherwise, so the sheet is a conductor. That takes us to a different kind of analysis, okay? So far, we're assuming that there's no medium holding it. Okay? We played this game for years in the career of an electromagnetic student, okay? Because once we put a sheet, the physics will change. Okay? Yes?
Like what we did with Gauss' law, we took the epsilon naught, I'm took it on the other side and we made a D symbol?
Aha.
We do the
That's when we will do that when we talk about two different media. Right now, we're not talking about an interface between two different media. Look very carefully. We're not talking about an interface between two different media. We're talking about an eye in a uniform medium, okay, in a current sheet. But yes, that's the direction we're going to go later on to complete the picture, boundary conditions, okay? So I'm done with this, right? I'm done with the magnetic field. Now, what observations can we make? We can make interesting observations. First of all, is that if I am here, 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 anywhere above the current sheet, will the field change? It will not change. This is bizarre, isn't it? Strange. Do you believe that or not? Well, this is the mystery of an infinite current sheet. The current sheet is infinite. If it were not infinite, that's not true.
I saw for the magnetic field there, but the magnetic field at which point?
I'm sorry, speak up.
Magnetic field at what point?
Anywhere. Anywhere. See this? This applies anywhere above. Anywhere above z equals 0, the magnetic field is constant. Anywhere below, the magnetic field is constant by pointing in the opposite direction. So now, right? Does that answer your question?
Yeah, which direction is it though?
I wrote it right here. Why? Y hat is in that y hat with a minus sign, meaning it's pointing in that direction. Okay? See, just 1 second. See, we have, look at this carefully, we have a field above the z equals 0 plane. We have a magnetic field pointing in this direction. Below, we have a magnetic field in this direction. Do you see that? Do you expect them to be continuous as you reach the z equals 0 point, z equals 0 point? No. Impossible. So they are discontinuous. They are discontinuous by what? By I. Do you see that? That will lead us to the boundary condition later on. So in other words, if you have a sheet that has a current, the magnetic field can never be continuous as you cross that sheet. Impossible. The discontinuity is precisely that I. Yes, sir.
So why do we say Z is greater than or equal to 0?
Thank you. You got me there. All right. All right? You're absolutely right. Okay? I stand corrected. See, I didn't say that's an excellent question. I corrected myself. All right. So now we take this and we move on to the solenoid. Okay? What is the solenoid? What is the solenoid? Can anyone tell me, have you ever seen a solenoid before in your life? A coil, right? So I want to find the field due to a coil like this. A solenoid, from a circuit point of view, is nothing but an inductor. You take a wire and you wrap it around your hand and you create an inductor. Okay? So I need to do the following. I want to find out the field inside of it, and I want to find out the field outside of it. Your book has an argument, in my opinion, it's not very convincing. Okay? So maybe that will get your attention. So how do we look at this problem? We take advantage of what we did right here. Okay? We take advantage of what we did right here, and I'm going to assume that the number of turns are so many and they're stacked next to each other. There's no gap between them. Okay? There's no gap between them. They're stacked very tightly. So right now I can represent this looking from this side. Actually, it will look like this, right? If they're tightly packed. But I can represent it more elegantly with I can take a cross section. I'm going to take guys, please. I'm going to take a cross section in this solenoid or this coil. So this is the coil, okay? This is the coil like this, okay? I'm going to chop it right in the middle along the axis of the solenoid, okay? And then I'm going to look from one side only. One more time. Guys, please. One more time. I'm going to take the coil here, chop it right in the middle, and look from this side. So what do I see? I see something like this. I see wires where the current is, let's say, going in. Okay? Going in means like this. Going in. So I see the back of the arrow. And then I see wires, or what appears to be wires, or current lines where the current is coming out. Okay? We assume that this is infinite for the purpose of coming up with something very simple, with a simple solution to the solenoid field. Okay? So let's start with this. This means that I have a current sheet that looks like a current sheet, right? It looks like a current sheet. The current is coming where? Going into the board. So the field that is generated by, I'm going to use by the black currents, I'm going to use the black marker to indicate the field. It will be pointing in this direction above this line and pointing in this direction below it. Correct? Just the opposite of what we did here. Because this one, the current was coming out. This one, the current going in. So I have uniform field going in that direction, uniform field coming in that.
This isn't infinitely long in set, like the sheet.
That's an approximation. I'm going to address that. I'm going to address that. It will work perfectly because you can think of it, you can take these as infinitesimal currents, okay? And just look at this plane, only at one plane, okay? Good question. All right, so what about this one? What about this one here? This will give me the opposite. In other words, above, I'm going to have a field going in that direction, and below, I'm going to have a field in that direction, because this scenario is the same that we discussed there, isn't it? It's the same one. All right, so what do you expect? You expect the field here. Wait a minute. What about here? What about here? I'm going to use the red marker to indicate the field due to the red current. I'm going to have a current like that, right? Above this, everywhere the current is going in this direction. Below this, below the black current lines, the field is going in this direction. So what do you expect the field above the entire solenoid to be? So this is the solenoid, the field above it to be very, very small. Why not zero? If we had an ideal situation, we had an infinite solenoid, it should be zero. But we have, let's say if we have a smaller solenoid than infinitely long, it will be very, very small. Here, we expect the field to be almost zero. In the middle, between the coils, we expect the field to be high. Okay? Convincing? To me, it is. Okay? The second thing is, how do we find the field? How do we find the field inside? Well, we use Ampere's law. Okay? I take an Amperian, some people call it Amperian curve or contour, and I integrate the B all over this contour. Along this contour, what is the integration of the B? 0. The field here is 0. So the integration above this is 0. So I'll end up with integration of the B dotted dl along this contour. I'm going to indicate it as C1 equals 0 plus 0 plus 0 plus the integration along the, let me actually label this as C sub x, only the integration over C sub x. Karina, you look not happy. Why? Everybody with me or not? No, she's not happy at me. She's not happy at integration over Cx. What is the integration over Cx of B dot dl? I really don't need to do anything special. It's just the B. It's just the B multiplied by this particular distance. So let's say this distance is d. So it's the B, which is constant, multiplied by d. Right? All right. So that equals I mu I, which is enclosed by the contour C1. So I'm going to label it as I sub C1 multiplied by mu naught. What is the I that is enclosed by this contour? There's one I here, one I here, one I here, one I here. So there's n, if there are n turns, n, capital N turns between here and here, I have to use that n multiplied by I, because it's the same I, right? It's the same I, so you'll end up with n i's. N i's. I times n. Ni mu naught. Okay? So the I that is enclosed by C1 is n times I mu naught. Finally, if I did it correctly, I'll end up with B being n I mu naught divided by d. Okay? Okay. All right? So this is, now, is this perfect? It is not. Just 1 second. If I had infinite number of turns, this is very, very close, very accurate solution. But if I have 50, let's say, turns, we know that the field, something like this, the field will not be completely uniform at the end of the solenoid. It will be fringing like this. Okay? So this is a reasonable and simple approximation. You had a question?
So n is indicating the number of coils inside.
Exactly. Exactly. So n is the number of turns, equal number of turns. Okay? Is the number of turns. Yes?
Isn't actually n and d like real? N is a function of d, right?
N is a function.
N increases as d increases.
N is a function of d. It depends. I mean, I can have a thick wire, a thin wire.
But it should be constant like that, right? Like it should be some constant. I mean, like anywhere inside the coil, we should have a constant b. Because
Yeah. Yeah. B is constant here, right? But what is the value of that B? Do you see that? What is the value of that B? Look carefully. We assumed we used this infinite sheet approximation. It means that the current is, the magnetic field is not changing along that direction. That's another approximation, okay? Okay? So which direction is it in? In this particular case, it is in the, if this is, let's say, x, and this is y, it will be in the minus x direction. Yes?
So if the magnetic field is relying on distance, so depending on,
The magnetic field relying on distance.
right, because it's over 1 over d, yeah, it's over d, right?
Yes.
So, does that mean that the magnetic field, like between the two solenoids, where
It is constant. As you go along this direction, the magnetic field is constant.
wouldn't d change?
No. D is changing. D is changing, but N will change.
Oh, so the two will
Okay, this relates to his question, yeah. I will change. In other words, they could be, for instance, to satisfy both of you, you can have wires that are this thick. Let's say realistically I have this thick of a wire and I make a solenoid out of it, okay? Let's say the diameter of this is L, okay? Then definitely there is a relationship here, right? Between the number of turns and D.
Can we just call n over d the number density?
Absolutely.
Like the
Absolutely. In other words, you have, let's say, 50 turns per meter. That can be the turns density. All right? Make sense? One more thing before we conclude. What have I created with the solenoid? I created a situation where I have a magnetic field that looks like this. Okay? In this case, it's coming out of this and coming back. Coming from this, coming from this end of the solenoid and turning back. We don't have time to follow up on this, but next time we will look carefully at the analogy, at the similarity between what we've created here and a natural magnet. And I want you to think about one thing, if I may. Just to think about one thing. If I put two magnets like this, one magnet here and one magnet here, and this is the north-south, and this is the north-south. These two, we know that they attract, right? Do we expect the same thing here? If I put a solenoid and I put a solenoid next to it, fed in the same direction. Give it a thought and we will discuss it at the beginning of next lecture. Okay, guys, I'll see you tomorrow, right?